Hello, Christian. No, it's Mike.
Yeah. Hi.
No, yeah, I was calling Michael Rob a couple of times.
Oh yeah.
More than, how many times did I call? Maybe you observed it more than me. After you pointed out, I didn't. Oh,
Michael could feel deeply offended.
Yeah, I think it was like 4 or 5 times. But I had a mask on, so.
No, that's not the reason. I don't know what was the reason. But, yeah. My apologies. Yeah, yeah. Oh, you.
Hello.
Oh, the sound is faint. That's because some reason it didn't connect the HDMI properly. One of you is Michael?
Yes.
Yes, now it's okay. Yeah. Thanks. You're checking the audio. Thanks.
Oh, okay. Yep.
After school Archie Thai video.
Okay. So we have a homework and a midterm. Do you remember? And you have midterm 2. You don't get to write 2 midterms on the board. So this is around.
September 21st and October 12th.
That's because this was not on 21st, remember? This was on 14th. And this is due on September. No, this is due on September 21.
So the other one, is it due on 12th?
No, this is in class. By default, this is going to be in class. Again, we will, if there is any need to make it take home, we'll do that. Yeah. I would like to do it in class because at least one of the courses I'm not satisfied with the take home experience. That's my fault, it's not the students' fault. And design the right questions. Okay, so We were doing conservation laws in electrodynamics. Conservation law.
I gotta run that too.
And one of the first relation was concerning charge. Yeah, and say charge density, the time derivative of charge density. This is the local statement. At every point in space, you can think of it as a small, tiny, infinitely small, or infinitely small volume, and the charge inside that volume or at that point is conserved. And I write 0 here. That is to say that that's a strict conservation law in the sense that there is no source for charges and currents. Are we missing someone? Jordan and Khalid, right? Yeah. Yeah, so. Okay, so that's charge. And then we also talked about energy, electromagnetic energy. That should be, this is EM energy. Like we're not talking about other forms of energy here. How is the electromagnetic energy dispersed, if you want, charges? Again, local.
Can I say something about the exam?
Yeah, sure.
So,
Why should I ask you? Yeah.
So, in number 5,
Uh-huh.
there's this equation in somewhere. I think one of those equations is wrong.
Equations is
Can,
wrong.
can
Okay,
you,
that's
can you pull it up?
pull it up. Yeah, okay, yeah, I should be able to. Did anyone else notice there's an equation wrong? How do you pull this up? Hold on. Okay, exam. Number 5, you say?
Mhm.
Okay.
Down. There. Right in the cursor.
13B?
Mm-hmm. One of I think 13B is one. There should be R dot D times B.
This one here? This? Oh, I mean, others are not seeing it, right? I think Avinash is pointing out equation 13B in the homework, sorry, in the midterm, which is this term that I'm pointing in the cursor. Probably you guys don't see it.
You can share screen and you can see it.
No, let's not go there. Yeah, equation 13B, if you have access to it, just look into that. Okay. And what's your issue with that? So what are you saying? This is D?
Well, that equation cannot be equal to 3E and E at the same time, right? It cannot be equal to.
Oh, yeah. So you're saying 13A and 13B cannot be simultaneously correct.
Right.
True.
One
One
of
of them is wrong. Okay. But that's a hint. So what is the mistake, by the way? Can you point out?
I think in the second equation, B should be replaced with D and same D with B.
Okay, I think if I get this right, RBD. Oh, yeah. I see what you're saying. So D and B should be swapped, correct? That's all you're saying. Okay, maybe check. Right? I think Vinayak is correct. check equation 13b. And on the left-hand side, right? Left-hand side should be equal to d cube r dotted with
D.
d times b. Correct?
I think so.
Yeah, that's probably correct. I just cut and pasted that, and that's
If we do that and subtract equation 13a, if we subtract 13b from 13a, then we get 2e, which essentially gives us 1 over 2 pi.
yeah. Is that clear? Any questions on the side? Yeah, this seems to be correct. Yeah. But check it out. Good. Thank you. So no one has reached there. That means.
I haven't looked at number 5 yet.
Where is my?
Now we're gonna have to click
How do you?
overloop and click the expand button.
There?
Can you see here? Can you see loop in the minimize screen up there?
Oh, I see.
Go there and click the green button. Yep.
Green. Okay. Thank you. Yeah, I will struggle with this. Okay. Okay, so yeah, good point. Any questions, anyone else on this? Clear. Okay, so going back to what I was talking, conservation loss. You have charge conservation and energy conservation is given in terms of the energy density at a point in space that one has to imagine it as an infinitely small volume, plus divergence of the Poynting vector, which is a flux of energy. Again, this is charge density. This is the flux of charge density. Here we have energy density, flux of energy density, plus the source or sink of energy, which is the power, the energy lost into charges per unit time. That's like force dotted with velocity, and that's the power. And I should define these things. U.
Can we
Yes.
stick with small u because we've been using
Oh,
small
we
u?
did use small. So small u is equal to half E dotted with D plus and D here is epsilon naught E and B is equal to mu naught times H. The Poynting vector is E crossed with H. All these are position and time dependent. So let me not write it every time. It's much more compact that way. And we would like to do something similarly for linear momentum. Oh, So I was wanting to actually bring that small gadget, or what is a small device that you might have seen. What is this called? There's a radiation pressure instrument. Right, a small 4 leaves inside a small vacuum jar, and if you shine light on it, it actually moves. Let me bring that. That's actually a nice thing to. Have you guys seen?
I have one of those.
Yeah, you must be having it. Let me quickly bring it. I think it's a good enough demonstration that it's worth spending 3 minutes. Kept it on the table.
I think he's talking about a Crookes radiometer.
Yeah.
Yeah. So I have a question from the TA side of things. That quiz that is on the schedule for the physics labs. This is just me, but we got nothing on that other than it was a quiz.
Yeah, we didn't get anything.
When I asked him, he said we were supposed to write them ourselves.
Yeah, that's what, at the last TA meeting, that's what Scott said. I think he, just like 2 or 3 questions, shouldn't take more than 15 to 20 minutes. It's just like a review of the material we've covered up to that point. So I don't know. I haven't done mine. I haven't done my first quiz yet. I still need to do that. But I don't think it has to be any big deal. And then they should have at least a couple days to complete it.
Oh yeah.
Yeah.
I
So
haven't done my
yeah, I
quiz
don't think they
either.
gave us any
Yeah,
direction
same.
as
I
to how to
didn't-
do that. Yeah.
Yeah.
I was wondering if anyone else did that.
If I wasn't the new person, I would complain a little bit about the level of support that we have been given. Because Luke and Michael have not really done this before,
Yeah.
so you got kind of thrown to the wolves.
Yeah.
Yeah, you guys had to jump in.
I'm a little higher on the food chain, so I will irritate people if I have to.
Yeah, I don't know. I mean, I think the support's there if we ask for it. And I think it's probably a good experience to, practice writing quizzes and, practice giving short lectures and stuff. The best way to learn how to do it is just to do it.
Yeah, but I think the best way to learn how to do it is to do it with some guidelines in place instead of running out there. I mean, I've been doing this for 23 years. I can do this, but I kind of feel bad that others have not been given very much instruction.
Yeah, that's a good point.
I should say that this is sort of a cheat also. So it's an anti. This is of the demonstration.
My aunt had one of those that was we're talking 40 years ago.
40 years ago. Yeah. So this is about, I think, 140 years old. Yeah, the 1880s or
That
something.
thing?
Like this instrument, or what do you call this, an instrument or a gadget, or not a gadget, right?
I mean,
What's the word for it?
I'm not sure because she just had one sitting in her window and it's continually
Yeah, that's what I do. I keep it on the window, and every morning when I come, this is actually moving. So sunlight is strong enough that it'll, yeah. So if you can see this, usually it is still, you see the 4 leaves. virtually, can you guys see?
Yes.
Yeah. So if you shine light on this, it actually rotates and reasonably fast. I mean, pretty, let's say 5 revolutions per second or something, or let's 3 revolutions per second or something like that. And if you notice, one side is colored white and one side is colored black of this. And this rotates. So the idea is that light falls on the white side and gives a radiation pressure on it. And that's what makes it move. Any comments on that?
The one that I have actually spins in the opposite direction you would think.
That's a point. So the point is that remember Maxwell came up with his equations in 1865 or something, and almost immediately within 5 years, Maxwell himself said there will be light. You have the concept of light, and within 5 or 10 years, you had radio. I think Hertz demonstrated the first radio in a lab, like that's one corner to the other corners in a wireless manner. I think that was probably 75 or something. And within 5 years, I think they had, if I'm not wrong, cross Atlantic. If probably not cross Atlantic, I'm not sure when it crossed how they made it strong enough. But this is 1880s, so this was so immediately you write down these equations and you say, oh, there is momentum associated with electromagnetic radiation. That means you can use that momentum to move something. And this was considered the first demonstration that you can actually do that. Right? But then very quickly, there was a controversy that began that, oh, this is not a correct demonstration. And the idea is that it moves in the opposite direction, actually. So I'm going to, so what I did is, what you can do is you can actually take a heat pump and you show that, oh, you don't need a light at all for this. Instead, you can just do it with heat itself, and then I can tell you how it goes in the opposite direction. I don't know if you want to help me hold it. So no, you burn yourself. No. How do you show this to them?
Depends on how hot that thing is.
I think this gets hot. How can you show?
You can lift the camera down.
Yeah, that's it. That table is visible.
I don't think they can see
Yeah.
things inside spinning.
Can I guess see something? If it is going to spin, will you see it? You will not.
And what I say is,
Yeah.
we move the camera,
You move the camera.
put it down here, so they can see.
We'll have to set it again. Let's check. Hold on. Give me a second. Okay. Oh.
Because of Zoom.
Oh yeah. Can you zoom it? Use that. It may not zoom it to that. You take it remote. Okay. Just zoom. Okay, let's see. Do you see anything? I'm moving those.
Yes.
I can't tell. Is it spinning really fast? Oh, there we go. Now I can see it.
Outstanding, then.
Yeah.
Earlier? Okay. Stop. Yeah, now it should be. Okay. So, thanks so much.
Is that hair dryer?
Yeah, this is Jordan's. This was some project. I think, yeah, Moses was involved in that. I think there's a Dustin was trying to make gyroids out of plastic rods, and we were trying to blend it using those Jordans. Right. So the point is, this is called. So it's still. Okay.
Sorry, I'm late. I was working on the exam and lost track of time.
So I just mentioned your name, and you just show up. This is your hair dryer. I'm supposed to return that to you.
Oh, yeah, the heat gun? Yeah.
Yeah, you call. Oh yeah, not a hat iron.
Yeah, if you tried to dry your hair with that, I think you wouldn't have any hair left.
Good point. Yeah. I think
Maybe a hair evaporator or
Okay, so did you see the demonstration, by the way?
I didn't, but I'll watch it afterwards.
Yeah.
I'll watch it on the YouTube.
Okay. So here's an extra credit. And it's written everywhere. But still, I think there is, at least the way it is discussed, sometimes it looks controversial. So I'll filter your, whatever you read. So this is called the Crookes radiometer. So basically measures radiation, or it was proposed as if it measures radiation pressure. Radiometer. But that's a wrong name. The idea is that this is not electromagnetic at all. It is actually heat engine. So extra credit is to see what's wrong. In fact, analyze if you have this to be the black. So that's your axis. The dark shaded region is black and the other side is white. And ask the question that if you have light coming in from here, think of it as simple linear momentum problem. And notice the idea that white light will reflect the light that is incident on it, and black regions will absorb the radiation that's sitting on it. So if you assume that this incoming entity, if you want, or electromagnetic wave has a momentum, then the transfer of momentum is different on white and black. And accordingly, you can argue, is it going to move this way, or is it going to move clockwise or counterclockwise? So make that argument and then argue the same thing with heat. Notice that if it is a black surface, it will absorb heat in a certain manner, and then you have to talk about the differential heat, which side gets hotter, and use the thermodynamics of the fact that if it is hotter, then it tries to push on the surface, and argue that there are two different ways of rotations that will happen based on whether it is momentum or not, and make it clear, like justify or convince yourself about that. And I can come back and in the next class do that. Again, is that clear, Christian?
Yes.
Yeah. You should see the argument. The arguments should be available, but in this form of getting the momentum conservation, that probably is not available. If you search hard after everything is available. Okay, so that's something. And again, next week we'll talk about electromagnetic, how much energy and momentum is stored in an electromagnetic wave, also like a monochromatic wave. At this point, it is very general. We will specifically talk about an electromagnetic wave in either one of the classes or in one of your homeworks. So anyway, that was a small digression demonstrating that there is momentum in the electric field that we see around. We would like to get an expression for this, and for that, let's begin with the expression for force, the Lorentz force. So if you have a point charge, the expression for the force is charge times the electric field, and it depends on the position of the, so this electric field is evaluated at the position of the charge, plus Q times V cross B, the standard, that's called the Lorentz force. If we want to write this in terms of charge density, you would say force per unit volume. So this force per unit volume. Force per volume. And then this becomes a position dependent quantity. Position and time dependent quantity. And charge per unit volume interpreted as charge density. Let me write the dependence. Moment. Plus Q times V is the current density. That's J or comma P crossed with B. That's our force acting on the charge at this position R and T. Even though it's a charge density, it is a force acting at that point. But if there is no charge there is no force. Right? We want to write this in terms of electric field. So the simple idea is that replace all the charge density and current using fields using Maxwell's equation. So force density is equal to, this is using divergence theorem for the electric field. That's E plus plus J, right? J is if you use the fourth Maxwell's equation, then when I write it, the fourth is not really a universal concept. So this will be del cross H and minus time derivative That's good enough, but usually we know that there is a symmetric version in terms of the magnetic field also, right? And it is usually hard to get that at this point, especially with the signs involved. But let's see. So usually you will put a magnetic charge and that really makes it concrete. But we know that, imagine that there is a magnetic charge here, magnetic monopole charge here, rho m times the magnetic field times the current density due to the monopole times the electric field, that is 0. But it is 0, I can introduce that, right? So how do you put that as 0? So that's dotted with B. So this is 0, so I can add whatever I want to that, and I'll say this is H. Now the only challenge then is that is it plus or minus? Okay, so leave that open. So let's, for now, let's say it's plus. Okay. So I'm imagining that the magnetic charge gets affected by the magnetic field. And the same thing in here. You have is minus del cross E. Like again, there's a sign issue here, right? It's a 0, but then how do you know which one is which? It is minus dV by dt crossed with d. And I say that's plus. I think it is plus. I usually don't remember. Usually you can argue it using the dual transformation that we talked about. I think we did point out in the last lecture. Any questions? Why I got that? How I got that? So this is equal to 0. This is equal to 0 using the Maxwell's equation. So that's perfectly fine. Okay, that's just so that I can write some expressions associated with. Okay, so immediately notice that our goal is to write time derivative of something, divergence of something, and whatever remains we will interpret it as a source. We already see the time derivative in here. So this is equal to, clearly, minus, oh, probably not, right? This is d cross d, and that's d cross b. So I switch my sign. I switch the sign to be negative. Why did I do that? See, notice one is coming in b cross b and the other is coming in b cross d. So I would like to take the total derivative common, and so this is minus time derivative of d cross b. Because the cross product changes the sign, that makes it.
So shouldn't that term be del cross E minus partial B, partial T? Like, to me, that's not equal to 0.
What is not equal to 0? This one?
Yeah. Mm-hmm.
Isn't this Maxwell's equation that del cross? Usually, at least I, in the classroom, write it in this form. This is Faraday's law. Like rate of change of magnetic field, the negative rate of change of negative is the Lenz's law.
Oh yeah, that's right.
Yeah. So now if there are two possibilities, I can take this to the right hand side or bring this to the left hand side and say that's 0.
Okay.
That's you cannot say tell anything about the sign unless you invoke the dual transformation. With the electric and magnetic field, you can say that. And I chose that to be negative just to see this time derivative coming up. Okay, so that's so these two taken care of, these two terms taken care of, right? And then let's see down here, these two gets combined. Yeah, so let's keep that separate. Where am I? Yeah, so let's do this and this. So this is plus divergence of d times E, and here we have plus del cross E crossed with D. So that has all the electric nature in one place, and similarly we have plus del D times H plus crossed with B. And the claim is that this whole, all of these 4 terms can be actually combined into in the form of a divergence. Divergence of some quantity is equal to that.
Because del dot B is equal to 0, so you can make it a gradient of the a gradient of a.
It's not obvious here, right? What do you mean here? Is it tell that again, maybe?
So since del dotted with B is equal to 0,
Mm-hmm.
you can replace it with the gradient of some scale.
Yeah. So I think what you mean is no, that is that if del dotted with B is equal to 0, that means that B can be written as a curl,
Mm-hmm.
right? Yeah, that's true, but I don't want to go into the potential. That will involve new fields. Let's stick to electric and magnetic fields alone. Potential is okay, but that has its own complications of a gauge dependence. For some time, I will stick to fields. Eventually, we will get into the potentials, yes.
So
Is that-
since it's statics, then you wouldn't have to worry about the gauge stuff, right? Because
Oh, no, gauge dependence is always there, right? And we are not doing statics, by the way, at this point.
well,
There is time. This is complete E&M, actually. Did I mention that even in statics yet? Not yet, right? Because I do the undergraduate E&M also, it runs parallelly, so it is a little confusing to me that when did I say something in the class. So yeah, even in the static case, for example, I think what you have in mind is dotted with E, for example, or del crossed with E is equal to 0, right? It's statics. This is equal to derivative, this is equal to, and
you can replace that with the flux.
or the potential, right? Electric potential.
Mhm.
That's what you, right? That's okay, but then this is off, right? Electric potential is off by a constant.
But you're
Like derivative of something is equal to electric field. I can add and subtract a constant to this.
it's the
And,
same though once you take the derivative, right?
Yeah, so that's the problem. So the derivative is always killing something. So there is something you miss here. So that's the simplest form of gauge you can see. I mean, this is not very bothering, but that's a gauge dependence there, right there.
Gotcha.
The simplest form. Same thing here, derivative of something is b. It's in a curve form. Even a, you can add something to it, and it doesn't change, and that will be called as gauge dependence. But we will have to encounter it, but as of now, I'm just avoiding it.
Okay.
Like as far as you're in the fields, then you're safe from the gauge dependencies.
What is a gauge dependence?
Yes, please.
Oh, I said, what is a gauge dependence?
Oh, okay. Now that has come up, so that now we are going on a different track. Okay, that's fine. Let's go. So what is a gauge dependence? Okay. There are two Maxwell's equations. So there is two of the Maxwell's equation doesn't have a source in it. One is both related to the magnetic monopole, right? One is del dot D is equal to 0, and the other is del crossed with E. And this time, let me write it on the left hand side. B is equal to 0. Correct. If del dot B is equal to 0, it is convenient to write B is equal to del cross A. Okay. And that's a reasonable solution. But then you can immediately ask the question that is a physical. Like for example, if for a moment, I think if you want to, if this is not a very familiar topic or intuition is less with the magnetic vector potential, if you're in statics, by statics I mean time derivative is 0, then del cross E is 0, which is what we study in introductory physics. And this implies that electric field is equal to minus gradient of phi. Right? That's the electric potential, that's the electric field. This is the magnetic, we call it magnetic vector potential, and this is the magnetic field. And then you ask the question that, is phi physical? Can you measure phi? Electric and magnetic field you measure, but is it okay to say that we can actually measure phi, or more importantly, measure A? Electric potential, volts, right? Often you measure volt, there's a voltmeter, right? Right? How correct are this voltmeter in principle? That's what we are asking. And the point is that A and phi are not actually measurable quantities. That's a claim. You cannot measure A and phi. Then what do you mean? I mean, we have voltmeter. I just said you will be off by certain quantities. So let's see how that works. So let's get away from statics for a moment. This is still valid. Okay. So substitute this in here. So this is del cross with E plus time derivative of del crossed with A. That's equal to 0. And everything within Maxwell's equation, noted I'm not making any approximation or anything. If you see this equation, you have to trust that this has to be true. This should be possible in a lab. This is a curve, and notice time derivative and position derivative can be interchanged in the functions that we talk about. If not, one has to worry about that with that understanding that you can actually interchange those two quantities, and you immediately come across a relation E plus dA by dt is equal to 0. This is a generalized version of your del cross E. That's your Faraday's law in a sense. You say that Faraday's law involves a time derivative of a quantity plus the electric field. The curl of that is equal to 0. But if curl of something is equal to 0, you said that can be written as a gradient. So this is a curl of something being 0. So that means that you can write that as a gradient. So that's just a small generalization of that. So what's the conclusion is that as far as potentials goes, not yet gauge, del cross A, and so this is the magnetic vector potential, and this is equal to minus gradient of the scalar potential minus the time derivative of the vector potential. Okay, that's good. And then you immediately ask, as I pointed out earlier, are these unique? Is A and phi unique? Because if it's not unique, then there is a problem with experiments. When you measure an experiment, do an experiment, what is it going to measure? So let's see if this is unique or not. And you clearly see if it is static, this goes away. So let's consider the following situation. So let's say phi prime is equal to phi plus either it's plus or minus, I don't remember. It's del dotted with A minus plus d mu a mu. Yeah, one of them will be. This is
It should just be not the dot product, but just the gradient.
that's a scalar, right?
Yeah, so phi prime would be phi prime plus the gradient of, is that right?
It's for vector potential.
Scalar, right? So let's see. What I think you worried about whether I wrote it correct or not, d mu and a mu, right? So dA by dt a naught phi. Oh, it's a time derivative of phi.
Because A prime would be, it's because,
Oh, sorry. Yeah, I'm completely writing wrong. So there is no A. Sorry. Yeah, you're right. Okay. So this is how it is. Yeah, sorry. D by dt of there is something arbitrary, right?
some
This
constant.
is something arbitrary. Yeah. So, but this is position and time dependent, though, by the way. Anything. This is not just a constant in the sense of electric potential. Yeah, I wrote it wrong. Very sorry. Yeah. I was thinking of a scalar, but then not in terms of A and phi, in terms of something new. This is not A, this is is lambda. Okay? Arbitrary function, completely arbitrary, has nothing, no physics associated with it. So this is arbitrary. And it is a function of arbitrary. Thank you for catching me on that. And then I have to put a vector also, right? The same function, I take the position or the gradient of it. Yeah, good one. Okay, except for a sign, let's see what happens to the electric and magnetic field. So let's start with electric field. So the new electric field would be minus L of phi cos E by dt of lambda and minus of E by dt of A plus L of lambda. I can already see one of them has to be negative, right? I want to cancel this negative negative. So let's make this positive. Usually the time is better to be negative. I changed this. This was plus. This is plus. This is minus. Okay. So this is plus. This is minus. Okay. So everything remains the same. And minus dA by dt. Plus of that, minus of that, that's 0, right? So notice what is the implication here is that I can add this kind of a function and derivative of that and still not change the electric field, which means that my phi is not unique. Right? This is the non-uniqueness in that. Same thing with magnetic field, just for completeness, quickly do that. L crossed with a plus gradient of lambda. Curl is 0, so that's del crossed with A, which is your B, old B, and this is your old E. So the electric potential and the magnetic vector potential are not unique due to this this transform. These are called gauge transformations. Okay. So technically speaking, A is not unique, but anything you have heard about A in this context? Has A been ever measured?
No, but you use it to solve for magnetic fields when it's difficult to solve for the magnetic field, right? So you
Yeah.
just
Don't you,
But anything else you want to think about in literature if you're aware of? Maybe not.
don't you measure, like, I don't know if you really measure, but don't you like get something in terms of vector potential, like work done when a charge is being moved in a magnetic field, something like that?
No. A is, so as we pointed out, A is not physical, right? So you cannot do anything with A. But it turns out that there is one interesting feature that, for example, if you were to do integral of A, right? So A is not physical. So what if I measure a lot of A's? So this is a path dependent quantity, right? I integrate it along a path, a lot of A's, then it should be again unphysical, right? If A is not physical, I cannot measure A, I shouldn't be able to integrate along a path and do something different. So that's okay. But now let's consider a closed line integral. And that becomes interesting because now I can use Stokes' theorem and say that this is actually dA dotted with del cross A. And this is some surface that enclosed by that. And that's magnetic field. That's a flux of the magnetic field. So flux of the magnetic field has a clear meaning that can be measured. So better, a closed integral of A is still physical. Right? And there is a lot of, like at least first time when it was written, I think there was a lot of controversy over how can that be true, but it is okay. Like this magnetic field, so closed line integral of A somehow gets rid of this arbitrariness, and you can see that. For example, the L dotted with A. Let's see the arbitrariness alone, right? This is the what is the gauge dependence on this? So this is equal to the L dotted with. So this is A prime. Let's say A prime is A plus the divergence of some quantity lambda, right? That's your original EL dotted with A plus the divergence of this quantity. So this is DL dotted with the divergence of lambda. What is EL dotted with the divergence of a function, some random function lambda going from R1 to R2 along a certain path? What is this equal to? This one? No, that's not true. What is that equal to? Line integral of a gradient?
Oh, that's zero, right? Because
Oh, not zero.
how do you have a line integral of a gradient?
This way. What is, okay, can you guys see here? I cannot do that side. What is dx time derivative of the function f from going from A to B? Let's say x1 to x2. What is that?
X1 minus X2?
F of x1 minus f of x2, right?
Mm-hmm.
It doesn't depend on the path in the sense this is one dimensional, there is no path here. But I can go all the way there and come back here. That's okay. I'll still get the same integral, same values. Right? So now tell me what is this equal to? Let's see the analogy and tell me. Dx derivative. They cancel out in a sense. It's like saying you have a path, the boundaries of the path matters. It's only the boundaries of the path matters. It is independent of the path. Okay? No, not familiar at all? This is R2 minus lambda of R1. Okay, refresh here, maybe if you don't mind. Vector calculus is one of the first things you see in the vector calculus whenever you do it. You can explicitly do this and like in few steps show that. Okay. But that's good. But here it's a closed integral. If it's a closed integral, what happens is that R1 is equal to R2. Those two are equal, that goes to 0. It's like saying curl work done by a gravitational force when you go around a path. You can go all the way to another galaxy and come back, and still the work done by the gravitational force is 0. Yes.
That's why I was confused, because I thought for whatever reason that it was a closed.
Closed and
That wasn't a
because you want this to be 0, right? That's clear. That's because of this, right? So that's equal to 0, and that's clear. Right? And there is an experiment, or there is an experimental proposal that actually claims that this can be. So now, so actually, what is the non-triviality here? Okay, so let's since we got into this, and I'm losing all my time. But I think this is a good discussion. It would have happened somewhere else some of the time in the class. So there is this non-triviality here, or why there is a controversy in this discussion is the following. Now let's think of a thought experiment. Let's say there is a magnetic field coming out. So this is just a boundary. Think of a solenoid, right? Solenoid can generate this. Oh, you have to run away. So there is a solenoid, let's say, having a magnetic field going into the boat. Okay. This is an infinitely long a solenoid coming out of the boat. Right? So that's your B. So when you have a solenoid, what is the magnetic field inside the solenoid? What's the expression of the? So you see what I'm asking, right? There is a solenoid like this. A magnetic field inside is given by an expression mu naught times current times the number of turns per unit length. Correct? That is inside the solenoid. What about outside? That's inside. And it's 0 outside. Is that familiar?
Mm-hmm.
Right, so it is perfectly 0 outside. So we are talking about an infinitely long solenoid. Magnetic field is constant inside, uniform inside, and 0 outside. Okay. Now let us say that there is a charge Q that's moving with velocity V at this point here. What's the force acting on that charge?
The Lorentz force, right?
Q equals V.
Going up.
Huh? No, see
It's
this.
outside is 0.
Check this out. Right? What is the force on this charge?
Nothing.
Nothing, 0, agreed? Right? All of us agree that it should be 0 outside. Same thing here, right? Anywhere there should be 0. Right? Now, so this is the experiment. This is called, what is this called? Abraham? Yeah, Aharonov boom effect. So here is what they suggested, that let's say you take an electron, start from here, or let's say positive charge Q, right? And you have a beam of it, let's say there's a lot of electrons. They can go this way and they can go that way. In fact, let us take it to be all the way coming in here, right? And there is a screen here. Right. One would ask, why should it bend at all to begin with, right? So the point is, you don't expect this magnetic field to affect this charge to begin with. But the claim is that it will get affected because there is an A around everywhere. And A is not physical, but the line integral of A is physical in the sense that if you go all the way here and then come back in the reverse path, right, the electron, or I think better, let me say it this way. This is a thought experiment, right? I don't have to worry about how the experiment will be done. I take a charge, positive charge Q, and go around this magnetic field, right? And it won't come back in the same state. This has a physical effect associated with it. and that's related to A dotted with dl. The closed integral of this is not 0. Right, so it picks up a phase when the electron comes back to the
I
same
have
point.
one question.
Uh-huh.
So we consider vector potential is towards the clockwise direction.
Vector potential. I didn't say anything about the vector potential, right?
Well, if there is a magnetic field, there should be a vector potential,
Yes,
right?
so that's the solution for this. What is A for this field?
What I was gonna say is if we have the charge move directly down, let's say making
This way?
mhm.
Uh-huh.
So that means the charge will move perpendicular to vector potential, right?
But where is it? I don't know what is the direction of the vector potential?
But the magnetic field is crossed with it, right?
Yes.
Like the
So,
curl of it.
so yeah. So I think you're telling it ahead that this you expect it to be in the phi hat direction.
Mhm.
That's correct. That's correct. So it will be in the phi hat direction, and there will be some functional dependence on this. Let's say R. And so now you're trying to say that your claim is that if this is your phi, yeah, so that's your A, and if velocity is perpendicular to that, that's 0. But why velocity? Yeah, why are you calculating that? Okay. Go ahead. Maybe I'm not getting it.
No, what I was gonna say is, if it is moving perpendicular to the vector potential, then it should not experience anything, right? It should just go
Because
straight.
I think what you have in mind is the energy. Energy depends on B dotted with A. And yes, energy is change in energy is 0 when you go perpendicular to that. Yes, that's correct. Yeah. Yeah. But I'm trying to, yeah, that's correct. I would say if you go from here to there in a perpendicular direction, probably you get a 0. But you want to be careful there because A has even though this is in the phi hat direction, this has non-trivial features. Okay, this analysis shouldn't be done algebraic at a simple algebraic level. So typically you say there is a string associated with that, like there is a discontinuity line there. So be careful. So I don't want to go into that because I'm not prepared for this at all. This is a non-trivial effect. In many ways controversial because of that, because everyone, or there are traps here that you can fall into very easily. But what I was trying to point out, just a small thing I was trying to point out is that you can think of a charge going around here and get some non-trivial magnetic field effects in the face of the charge. So B shows up even though there is no force acting on that. Is that clear? So for example, this phase here, so the phase, in quantum mechanics, you talk about phase of the electron, let's say of the electron. This depends, or this is equal to the L dotted with A, which is actually the flux of the magnetic field. So even though this is not experiencing the magnetic field, it experiences the flux of the magnetic field, and which is not 0. So you go around and your experiment can see that, oh, I measured the magnetic field, but it didn't experience any force.
So you can measure the magnetic field based on phase changes.
That's the claim. I don't know whether experimentally this has been achieved. The point is that, again, when you make the measurement, there's always a controversy that, oh, this is not the right thing you're measuring. So it's a lot of, it's controversial today. People like to debate this a lot. But most of the, why should I say most? I think looking at it this way, it is okay. That's a correct effect. The effect is there,
So if you remove the magnetic field, the electron returns back to its position without a phase change. Okay.
Actually, the experiment is not done this way. You don't go around it. The way the experiment is done is the following. You put a beam of electrons. Right? So this is an electron beam. You put a solenoid. Reasonably simple thing to do, right? And if you were to put the beam, there is phases associated, you will see fringes here. You switch off the magnetic field, the fringe will go away. So it's like the double slit experiment steps. Pretty neat kind of. Okay, so we have a small issue here. In the sense, I went into a tangent. I'm going to postpone the homework to Friday.
Okay.
Because I haven't covered the stuff you need for the homework.
This was good. This was good. I like this.
This was good. I know it's good, but I have to cover also. Sorry, but yeah, I know. I also like it this way, but you have to be a little focused also. No, I'm not complaining to you guys. It's just I'm complaining to myself. How should I control my going tangent ways? Yeah.
I mean, you couldn't say we weren't. So it's beneficial.
Well, then again, you cannot say what
I said you couldn't say that we're not learning something that's important to this subject topic. So I feel like it's.
I completely agree. So this is the challenge, right? Yeah, I completely agree. This is hopefully every one of us agrees. But it's nice to have some systematic things also, right? Whatever everyone learns, also we should learn. Correct. I don't know. Yeah. So okay, let's actually at least do something, right? We have 5 more minutes. Yeah, maybe homework, extra credit. So we left the, oh yeah, Moses, I should get back to you. Moses, did I answer your question?
Yeah, you did.
Yeah.
My question was just about the gauge dependence, which you did answer. So.
Yeah, so that's a pretty detailed view of gauge transformations, and there are important things also associated with gauge transformations. The mass of the photon is in a complicated way dependent on the gauge transformation. If not for the gauge transformation, if not for the gauge freedom, you could say, there is this freedom associated with the choice of A and phi. If not for the choice, if not for the gauge freedom, photon would have mass.
Okay.
So it should be of this kind.
It does have a gauge dependence, or it does not have a gauge dependence?
There is a gauge dependence.
Okay.
And it's called the gauge freedom.
Okay.
Like I can choose my A and phi up to a certain gauge and still get the same answers.
Gotcha.
And that freedom leads to photon not having a mass. That's not obvious at all.
Okay.
Like you could always say, does photon have a mass? How do we know? To great accuracy, our measurements, it is not having a mass. But then using symmetry principles, you can show that, or it turns out that gauge freedom leads to massless photons. Yeah, that's not obvious. That's an advanced topic. But yeah, so there is this relation. So we were doing the force or conservation of momentum, and we got this expression there, right? Plus L crossed with E or crossed with D. Show that this is can be written as a total divergence.
Is that extracted?
Yeah, why not? Extracted, yes.
No. Maybe they should show that, so I was wondering if it was.
Yeah, since like I'll come back and do this next time. But let's say extracted it, dotted with. So this is a vector, right? So if I write a gradient, it has to be a diagonal, right? So let's say M. Right. Find M. Find minimum, right? Okay. That's all. It's just attempt on it. It's not a very, if you're not able to do it, don't worry about it. We'll do it and that class next time. Thank you.
Thank you.
Yeah.
Thanks.
Yeah, thanks.
I had a question, but I can't remember what it was anymore. Just leave it at that.
Hey, Jordan, you just made my day.
Yeah, that's what happens when your brain begins to get older. There's something I know I wanted to ask, but it's just not there anymore.
Yeah, it happens to me sometimes.
Go. Something else takes my attention, like a fly flying by. Looks like it's kind of injured, and I'm thinking like, well, what happened to the fly? You know, did it land on something and get smacked, or?
Well, even if I don't think about anything else, I just forget.
You know what I found interesting to mention flies? When I went to, before I came back to school to get my undergraduate degree, I was kind of like a vagabond traveling around and living off of the earth essentially. And I got really big into mountain climbing. And what I noticed is that the flies in the mountains are very easy to catch and very easy to smack.
Yeah.
Ah,
And I guess it has to do with elevation or whatever. And
It is
Not
because
oxygen.
the air is thin.
yeah, they are extremely easy to smack. So there's almost no nuisance problem with insects. 'Cause if they get on you, you just easily take them out if you need to. But down here in Missouri, the insects are massive, and there's no catching them.
Mm.
When you
nice.
feel like a ninja whenever you get a fly.
If you see a fly, you know what you can do?
What's that?
If you have a spray, any spray, just
Mhm.
spray over it, and then its body gets wet and it cannot fly as fast.
So I just found out this past year that my father-in-law, if you have a bunch of wasps or so they have like a wooden house and they had like a giant wasp nest that I guess the wasps had made inside like a hole inside their house. And if you take soapy water and you put warm water and soap together, just like Dawn dish soap, and you throw it on their little home, they just all die because I guess the soap gets on their body and prevents them from, I guess, breathing. I'm not sure how they breathe, but I know it's like through their.
Yeah, I think the wasp they breathe through their siphons. I think that's what it's called. Siphon.
Well, that's a good non-toxic way of,
Yeah,
your wasp.
yeah. Instead of just spraying that stuff, it kills everything that is
Yeah.
within 100 yards.
Yeah.
So I was shocked. I was like, there's no way that works. That's an easy solution. Because every time, when we'd have issues with insects at my parents' house growing up, we'd call in the exterminator and he'd come in with all these like super toxic chemicals and kill everything. And then they're like, well, we never called anybody. We just used soapy dishwater. And you prepare it in like 10 seconds, you throw it on them and everything dies instantly. And everything around it's fine or whatever, but yeah. So, little insight.
Yeah, good to know.
Yeah, yeah.
I can't teach you about vector potentials, but I can teach you about flies. And
No, this is useful. This is useful. Yeah.
alrighty, thanks guys.
I'll tell my parents.
Yeah, tell your parents. Yeah. All right, bye.
Okay, bye guys.
Take care.
Bye Moses. Bye Elia.
Bye.